Section 4.6, the fundamental theorem of calculus. So far, we have seen antiderivatives, and we have also learned about the Riemann sum. The antiderivative, we know, is denoted like this. And whenever you see something like this, we are talking about the family of all the antiderivatives of the function f of x, which we can denote with uppercase f of x. And then we have plus c, which is an arbitrary constant. For example, if you have this notation, it means all the possible antiderivatives of x to the power of 2, which we know is 1 over 3 x to the power of 3 plus c. The other thing we talked about was something like this. If we said that is a very, very different concept from this one. While this is called an indefinite integral and it is a family of functions, this one is called a definite integral. And basically what this is, it's an area. It is an area like this. So you have a function f of x, and we have these two vertical lines, x equals a and x equals b. This notation here represents this area. The area under the curve f of x, above the x-axis, and between the two vertical lines from a to b. And the method we use in order to find this area was something called the Riemann sum. And the definition of the Riemann sum is the limit as n approaches infinity of sigma I from 1 to n f of xi times delta x, where delta x is b minus a over n, and xi also has a formula that's going to be a plus I delta x. So I'm going to write them down. B minus a over n, that's the delta x. And then each xi is going to be a plus I delta x. So today we're going to learn what is the relationship between these two concepts, antiderivative and the area under the curve. What is the relationship between the indefinite integral like this one and a definite integral like this one? The relationship is that you can find this area just using one antiderivative of the function. That is, you don't need to do this tedious process of the Riemann sum, the right endpoint Riemann sum for every function, as long as you have one antiderivative of that function. So that's the relationship between these two, and that's why you can see that the notations are so similar. So this is the fundamental theorem of calculus. It says, let f be a continuous function on the closed interval from a to b. Then this definite integral, which is going to be this area of the region, let's say R, is going to be simply f uppercase f of b minus uppercase f of a, where uppercase f is any antiderivative of the lower case f. That is, f prime of x is lowercase f of x. So, for example, if I am interested in knowing, let's say, integral from 1 to 3 of x to the power of 2 dx, I don't need to use the Riemann sum in order to get this area, because I know one antiderivative of x squared. One antiderivative of x squared is 1 over 3 x to the power of 3. So this is going to be 1 over 3 x to the power of 3, 1 to 3. And this is the notation for the value of this function at 3 minus the value of this function at 1. So the answer is going to be the value of this function at 3. So 1 over 3, 3 to the power of 3, minus 1 over 3. If I plug in 1 into this, I get 1 to the power of 3. And if I do these calculations, I'm going to get, this is going to be 9 minus 1 over 3. And if I do 9 minus 1 over 3, I get 26 over 3. So that's much faster than the Riemann sum. Don't you agree? Okay, do we understand the fundamental theorem of calculus? Any questions? Okay. So again, if you're trying to figure out this area from A to B, f of x dx, and if you know one antiderivative of the function f of x, so let's say that one antiderivative is uppercase f of x, so that the derivative of uppercase f is lowercase f. If you happen to have one antiderivative, then this is simply the value of that antiderivative function at the end of the interval minus the value of that antiderivative function at the beginning of that interval, and that's it. Of course, it doesn't make the Riemann sum redundant, because there are some functions where you don't have an antiderivative. Like, for example, if I give you this function, let's say from 3 to 8 of e to the power of x squared dx, this function, e to the power of x squared, it does not have an antiderivative. Simply, no antiderivative exists for e to the power of x squared. So if I want to calculate something like this, then I have no choice but using the Riemann sum. So this theorem does not make the Riemann sum redundant, because there are some cases where your function does not have an antiderivative. But as long as it has an antiderivative, it's going to be very easy to find that area. Just evaluate the antiderivative at B minus the antiderivative at A. Let's look at some examples. So in example 1, the area that we are dealing with is this area here, the region R, integral from 1 to 3 under the curve y equals x. So since this is a rather regular shape, you can just divide that into two regions, a rectangle and a triangle, and calculate that area. Or you can use the fundamental theorem, because we know that one antiderivative of this is 1 over 2x squared. So I just need to evaluate this at 3 minus evaluate the same function at 1. It's going to give me 9 over 2 minus 1 over 2. The answer is going to be 8 over 2, or 4. Is that clear? Okay, let's do another one. We are trying to find the area of this region, the region R. This is the area under the curve y equals x squared. Y equals x squared from 0 to 1. So basically, we are looking for integral from 0 to 1 of x squared dx. I just need to find one antiderivative of x squared. 1 over 3 x to the power of 3 from 0 to 1. Then I need to evaluate this at 1 minus evaluate this at 0. It's very clear. If I plug in 1 into this, I get 1 over 3. If I plug in 0 into this, I get 0. So the area is going to be 1 over 3. It wouldn't be that fast with the Riemann sum. Another example. I'm looking for the area of the shaded region R, which is the area under the curve x squared plus 1 between the two vertical lines from x equals -1 to x equals 2. So I'm looking for this area from -1 to 2 x squared plus 1 dx. I find one antiderivative of that. I need to evaluate it at the two ends and subtract. If I plug in 2, I get 1 over 3, 2 to the power of 3 plus 2 minus 1 over 3 minus 1 to the power of 3 plus minus 1. So it's going to be 8 over 3 plus 2 minus, this is going to be minus 1 over 3 minus 1. So this is 9 over 3 plus, if I add up these, I get 3. So it's 3 plus 3 is going to be 6. So the area is exactly 6 square units, depending on what the unit is. Could be square centimeters, could be square meters, could be square feet, depending on what the unit of measurement on the two axes are. Any questions? Another example. It says evaluate this definite integral from 1 to 3x squared plus e to the power of x dx. Geometrically, we know what this is. Yes, this is the area under this curve between the two vertical lines from x equals 1 to x equals 3. The region is not given, so we are just trying to evaluate a definite integral. So let's find an antiderivative of this function. It's going to be x to the power of 3 plus e to the power of x, 1 to 3. Evaluate this function at 3, I get 27 plus e to the power of 3. Evaluate this function at 1, I get 1 plus e. Simplify 26 plus e to the power of 3 minus e, and that's the answer. You're going to give me the answer in the exact form. So generally in web work or in the test, you're supposed to give the answer in exact form. You're not supposed to use a calculator and find an approximation and round it. You give me the answer in the exact form. You're using the symbol E, because E is an irrational number, and so it's impossible to write it down in exact form as a decimal number. So the only way to express that as an exact form is the symbol E. So in web work also, you just need to enter E, or for pi, you enter pi. Any questions? Okay, let's do example 5. The definite integral from 1 to 2 of 1 over x minus x to the power of negative 2 dx. That's example 5. We find one antiderivative of that, ln of absolute value of x plus 1 over x from 1 to 2. Because if I add 1 to this, I get negative 1. So negative 1 over negative 1 is positive, and then x to the power of negative 1 is 1 over x. Then I need to evaluate this at 2. ln of 2 plus 1 over 2 minus, evaluate that at 1. ln of 1 is simply 0, so the answer is going to be ln of 2 half minus 1 minus half.